Everyone can solve the first integral, but can you solve the second integral? That's the problem for this video. And before I begin with the second integral, let me show you how we solve the first one. So basically, this is a well-known integral that x to the power s minus 1 by e to the power x minus 1 dx. This is actually equal to gamma of s Riemann zeta of s. So that's why this will be equal to, now this is 2 minus 1 over here, yeah, that's why gamma of 2 Riemann zeta of 2 and gamma of 2 is 1, Riemann zeta of 2 is pi square by 6. So the answer is pi square by 6. Yeah. Now if we have to solve this, our approach would be first of all we will try to get a geometric series by dividing numerator and denominator by e to the power x. Yeah, and so we have e to the power minus x, e to the power minus x by 1 minus e to the power minus x. Now for x going from 0 to infinity, the modulus of e to the power minus x is less than 1. So that's why we can now write this as geometric series from n equal to 0, okay, from 1 to infinity e to the power minus nx, because the first term is e to the power minus x and ratio is also the same. Now we can take this constant inside and interchange the sum and integral from the dominant convergence theorem, and so we have x to the power s minus 1 e to the power minus nx. Now we can use the Laplace transform formula, yeah, for x to the power s minus 1, and that gives us gamma of s by s to the power n. Now this is just gamma of s, and okay, wait, not s to the power n, this is n to the power s, I'm sorry. So n to the power s, and this is just gamma of s times Riemann zeta of s. So this is the proof for the infinite, if the second limit of integration is infinite, yeah. But over here this is not the case. We have a as the second limit of integration from 0. So up to here, up to this point, it will be same, but after that we cannot use the modified gamma function, or let's say Laplace transform formula. And how do we do? Let's see it now. So basically this will also get converted to 0 to a x, and then sum from n equals to 1 to infinity e to the power minus x dx. Yeah, after that we have sum from n equals to 1 to infinity, yeah, and then integral goes from 0 to a, and then we have x, sorry, this is minus nx, and then e to the power minus nx dx. Okay, so if you can't use Laplace transform, what you can do is you can use integration by parts. Yeah, so we have sum from n equals to 1 to infinity. Now this will just be x, let us say this is u and this is b, and then e to the power minus nx by minus n, yeah, and minus integration from 0 to a. Now derivative of x is just 1, yeah, and integral of this is e to the power minus nx by minus n dx. Okay, now this is all inside the sum, and this is going from 0 to a. Okay, now this is a sum from n equals to 1 to infinity. Now this is just a e to the power minus na by minus n, yeah, and at 0 this will just be 0, so plus 0, yeah, because we have x over here, that's why that will just be 0. minus. Now if you have to integrate this, it will be e to the power minus nx, again minus n over here, that makes it n square. It goes from 0 to a. Okay, now this is sum from, okay, don't confuse this as b. Yeah, this is minus n. Okay, now sum going from n equals to 1 to infinity. This is, okay, so this is minus a times e to the power minus a to the power n by n, and there's reason why I'm writing it like this. And then minus, now it will be e to the power minus n a, so minus a to the power n by n square. And now at 0, this will just be 1 by n square, but minus minus will be plus. Yeah, so 1 by n square. Now you might know that Li s of g is actually sum from n equals to 1 to infinity g to the power n by n to the power s. Yeah, so we will use that, and that gives us n equals to 1 to infinity. And let me not write the sum now because I'm going to use this property, definition, not property. So this is Li1 of e to the power minus a. Yeah, and over here this is Li2 of e to the power minus a, and this is just Li2 of 1. Yeah, okay, so now now Li1 of this is, now I can we know that Li1 of Li1 of some g is just minus ln of 1 minus g, and also Lis of 1 is just Riemann zeta of s. So we will use these two properties. So first, using this first one, now this will be minus ln of 1 minus e to the power minus a, and then minus Li2 of e to the power minus a, and this will just be Riemann zeta of 2. Yeah, so our answer will be pi square by 6 plus a ln of 1 minus e to the power minus a minus Li2 of e to the power minus a. And don't forget, okay, so this is the answer. Now when we want to tend a to infinity, let us see what will be the answer at a, when a goes to infinity. If a goes to infinity, pi square by 6 will be as it is. Now this will be this will go to 0 because e to the power minus infinity is 0, and ln of 1 will then be 0. 0 minus, we will have Li2 of 0, and Lis of 0 is always 0. So you see the answer is pi square by 6 itself when a goes to infinity, and that was what we got earlier. Yeah, so we have basically solved the general form for this integral. Yeah, and if we have to talk about the flow, first of all, it was same. Yeah, we had to turn it into geometric series, and then used integration by parts. After using integration by parts, we got in the format of Polar logarithm functions, and we changed some of the special Polar logarithm functions into their other normal forms, and then we got the answer. So that was it. Hope you enjoyed this video and learned something new, and thanks for watching. Look forward to seeing you in the upcoming videos too.